Okay, so this is the solution video for the second portion of the Part 2 problems from topic 9.1, simple harmonic motion. Starting with 8G, that would be 8G, 8H, 9A, 9B, 9C, 9D, 10A, 10B, 11AI, 11A double I, 11BI, and 11B double I. So let's proceed to 8G. With a cable that's going through the magnetic field and inducing a voltage and all of that jazz. You can go back and read back in the problem to get the context of the situation. It seems to be a satellite stuff. About you can always go, but that's it says that the cable acts like a spring. Satellite Y. You give the mass of satellite Y. Under certain circumstances, Y will perform SHM with a period of 5.2 seconds. Again, if you're wondering what the heck they're talking, the context. But now we're talking about SHM, and so that's relevant to topic 9.1. So 8G says, estimate the value of K in the following expression, and we have the period of a mass spring system. So let's proceed from there. Okay, so let's explain 8G and 8H. So 8G uses the formula they give you, which is kind of nice because the formula is actually in the data booklet. They give you the mass and the period, and you just have to solve for K, and that's 3 marks. So not too shabby. The 3 marks would be displaying the equation without any substitution. So that would be, let's see, this mark 1 is right here showing the equation. Mark 2 is the answer, and then mark 3 is the units. Okay, so 8H, describe energy changes in the satellite Y / cable system during one cycle of the oscillation. And so we have the cable, which acts as a spring, so I kind of sketched it over on the right as a spring. And we have 2 masses relative to each other, and they probably oscillate back and forth around one center of mass, but it probably makes sense just to use the viewpoint of one satellite being stationary and the other one in motion. It just changes the reference frame. I find it easier to explain. But it says, since the system's in SHM, satellite Y exchanges its kinetic energy for the potential energy in the satellite X cable system, and then back again. And then that exchange happens twice. So that's 2 points is describing the exchange, and then the second point is saying that it happens twice. So that's the explanation in the box, but over here on the right, I drew a little sketch explaining what I'm talking about. So to start, I am going to keep this satellite, maybe that's satellite X, I'm going to keep that guy at rest, and then I'm going to consider that the satellite Y is in motion. And it doesn't really matter. It's there. They can be both in motion, but it's in terms of the energy exchanges, it doesn't matter. So when we begin the cycle, we have the spring at maximum compression, and then neither box is moving. So with the spring at maximum compression and no speed, there's no kinetic energy, and it's all potential energy. But then as the spring releases, all that potential energy translates to the kinetic energy of satellite Y, and satellite Y goes flying to the right. But then in that process, it starts to stretch the spring out. So the spring is not being compressed; it's being pulled. The spring is at tension, and so this block Y then stops again as the spring is fully stretched, and all that kinetic energy here then becomes all potential energy. And so that's what I mean, that potential becomes kinetic and then back again. That's the and back again. But that's only half of the cycle because the spring is at maximum stretch. So now that maximum stretch spring is going to pull satellite Y back, and that gives it a velocity actually to the going inwards, maybe to the left in this case, the way I'm drawing it, and it's all kinetic energy again. And then finally, all of that kinetic energy compresses the spring, and becomes all potential energy once again. So yeah, that exchange happens twice. Now, you don't have to explain all of that in order to answer the question, but I wanted to explain what the mark scheme is saying, because basically the answer, what I wrote down, is what the mark scheme says, but I wanted to explain it, so there you have it. So that's 8G and 8H for a total of 5 marks. Block by, oops. And then we proceed to 9A. So here we have number 9, and number 9A says, what are the conditions for an object to perform simple harmonic motion? There are 2 marks because there are 2 conditions. So first, the acceleration of the object is proportional to its displacement, and then the object acceleration, the direction of the acceleration is of sign opposite of displacement. And here's the equation for it. We have that the acceleration is equal to negative omega squared x. So here is the directly proportional piece of it. A is directly proportional to x. And then here is the negative, that the acceleration is negative whatever the displacement is. If the displacement is itself negative, then negative of a negative is a positive. So it's opposite sign. So 9b, they have the mass attached to a spring. They give you the mass, they give you the period of the oscillation, and it says like a wooden block attached to the same spring oscillates with a period of 0.74 seconds. So but they give the properties of the mass, but then they talk about this mystery wooden block, and they want to know the mass of the wooden block. So there's 2 different ways you can do this, but it all revolves around the period of a mass spring system. So there's our equation. Now, you're comparing 2 different systems, 2 different masses. It's the same spring constant, that K on the bottom, that's the spring constant. It's the same spring constant because it's the same spring. So really we're just kind of comparing mass of the system to the period. And so if you square both sides, you get that the period squared is proportional to the mass. And so really you could set up a ratio to do this all in one shot. And so you could say for the first period squared is to the first mass, as the second period squared is to the mass of the wood. And then the only thing that's unknown there is the mass of the wood. That's one way of doing it. I kind of like, with systems like this, just keeping it simple, using the known information to solve for, like for instance, the spring constant, and then use that same spring constant, because it's the same spring, to solve for the mass of the wooden block. So here's that. Alright, so we're solving for K. They give us the mass. Oops. They give us the mass right here. They give us the period right here. So I stick those in for M and T, and I'm solving for K. I did the scratch work over here on the right margin, and we get a spring constant of 27.7285, blah, 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 newtons per meter. And then I use that spring constant with the new period to solve for the mass of the wooden block. I'll keep some of the same scratch work for before, because now I'm actually solving for M. Actually, I just realized that I'm writing this as scratch work on the side. I should probably be putting these substitutions into the actual box itself. I also used the wrong period. So yeah, let me fix that. So yeah, all of this is wrong, but I threw it into the box anyway. And we wind up with a mass of 0.39 kilograms. Either way, the mass of the wooden block is 0.39 kilograms, no matter how you solve for it. Okay, let's move on to 9C and 9D. Yes, wooden block. It was not the original mass. Mass of that wooden block, we just solved for it, good thing. Again, error carried forward. If you couldn't do the mass of the wooden, no, I didn't solve 9B. This question, the period's also given there, 0.74 seconds, so I'm going to need back to the mass of the block calculation right there. Okay, 9C, they give us the displacement right here. Here's my pen. There's the displacements right here, and you're looking for the total energy in the block for the SHM system. And we know that total energy is 1/2 m omega squared, amplitude squared. So we're still talking about the block. I'm assuming that's the wooden block. Let me check that. Wooden block. Okay. We need block, and you needed it. In this formula, you could make up a number. That's not ideal, but don't, like, if you're like, now I can't solve 9C, so I guess I'm screwed. No, don't be like that. It's better to make something up and proceed than to just throw your hands up in the air. We pretty much have everything. The only thing we don't have is omega, but we can solve for omega because we know the period. So I went and saw for omega. I'm sure that's 1 point out of the 3 marks, 1 mark out of the 3 marks. I used the mass from that as well. That's what I used for the period in solving for omega. The amplitude is given to us in the problem, but our answer is going to be in joules, and joules assumes that displacement is in meters. So I went from centimeters to meters, hence the 10 to the negative 2. Run my numbers. And we wind up with an answer of 0.032 joules, or 3.2 times 10 to the negative 2 joules. Please don't forget to square when running your calculations. Very common careless mistake. Okay, next. 9D, very interesting. I think that this problem has been going swimmingly up until now. Springs in parallel. I was discussing this with Miss Coleman and Mr. Fitzpatrick, and we're not entirely sure that springs in parallel is even in the IB curriculum. Fantastic. But, you know, it's like some of these questions are easy, and some of them they make to be particularly challenging. And putting springs in parallel actually makes the system stiffer. It actually increases the kind of like the net spring constant of the system of the springs acting together. So it says fractional uncertainty in the mass of the block. So it's actually, and so looking at this equation for mass, the even though we're talking about a change in the spring constant, once that spring constant is changed, it remains constant for the system. But the period is a variable, and the period is 2 pi radical m over k. And by increasing the spring constant, that would decrease the period. Alright, so yeah, this is a toughie, but let's walk through it. So as I said, having parallel springs, first of all, you have to realize that that's going to increase the spring constant by having the spring placed in parallel. Actually makes the system stiffer. If you didn't know that, I don't know what to tell you, I apologize, but that would have been discussed or covered in SL. So I'll just blame Coleman. Anyway, so, no, I'm kidding. But anyway, so as spring constant goes up, then the period would go down because of this equation here, right, the period of the system. So that would, increasing the spring constant would yield a smaller period value. That's where I'm getting that from. And so then if it's a smaller period, but it's that same absolute uncertainty in the period, then the fractional uncertainty in the period would therefore be greater because you're taking the same portion of a smaller number. And if that fractional uncertainty in the period is greater, because of this equation here for the mass, if the fractional uncertainty in t is greater, then the fractional uncertainty in the mass will also increase. And so that is the answer. The fractional uncertainty in the mass increases. If you thought 9D was more difficult than 9A, B, and C, I would agree with you. That's also it for number 9, so let's move on to 10A. Here's 10A, outline conditions necessary for simple harmonic motion to occur. Again, these are separate problems on separate exams, so as I said, if they're talking SHM, they usually like to open it with defining conditions. So here's like the quick and dirty version. Acceleration is directly proportional to x. Acceleration is negative relative to x. The formula is a equals negative omega squared x. If you want something prettier, C 9A, because it's literally the same question. And then you could say, if this, was a graded assignment, why am I giving you the same exact question? That's a good question. I don't know, call it a freebie. And then you could say, well, what if I didn't know what 9A was? I'm sorry, if we're talking simple harmonic motion, you should absolutely know the conditions, the two conditions that define simple harmonic motion. That's like step 1. 10A is, and also with number 10, we have 10B. So this is interesting. It's one of these wave generators. So we have a buoy and a cable, so as the waves go by, the buoy moves up and down, and it says that the motion of the buoy is simple and harmonic. What a shocker. So things that we know. In the description, it doesn't tell us anything data-wise, but in the problem it gives us the amplitude and the wavelength and the speed of the wave. That'd be the wavelength of the waves, the water waves. And it says calculate the maximum vertical speed of the up and down speed of the buoy as it oscillates. So for the speed, now again, don't be confused. We have the wave speed that's happening, but we're talking about the speed of the buoy, the maximum speed of the buoy as it oscillates in SHM. So the speed equation we're interested in, and the formula is, well, let's put in the plus minus, even though we're talking about speed here, so it's just going to be positive. But plus or minus omega, and then we have amplitude squared minus the displacement squared, but we're talking maximum speed. And we know that for an SHM system where the displacement is 0, that's when the speed is at a maximum. And so if we set x equal to 0, we get that the maximum speed is v naught is omega x naught. Why do they use naught to denote maximum? I do not know, but that's what we're going with. And we do know the amplitude, it's 4.3 meters, but what we're going to need is omega. So a little tiny bit of gymnastics here. We have omega is 2 pi over the period. That's on the data booklet. And we know that period is 1 over the frequencies. So we then know that omega is 2 pi times the frequency. Why do I care about the frequency? Because I know the speed of the wave and the wavelength of the wave, and I can get the frequency from that. Granted, this is a little bit of SHM. This is, I'm sorry, SL, I was meant to say. But it's V equals F lambda. It's kind of a big deal. I think that's like not unreasonable to bring in here. And so our angular frequency is 2 pi speed over wavelength. So let's figure out what that omega is. So we have our omega, it's 0.61, etc., radians per second, and so we bring that into V naught equals omega x naught. We know the amplitude, it's given up here, amplitude 4.3 meters, and we wind up with a maximum speed of 2.6 meters per second. If you're thinking that's simpler than 10b, that's right. There are going to be some simple things, there are going to be some not so simple things. So let's keep going. Okay, number 11. So this graph is pretty funky. So it's representing a longitudinal wave. Yes, I know it shows a transverse wave, but bear with me. So the x-axis is the actual displacement forward in space. And then the y-axis, that's the distance that the wave travels. And then the y-axis shows the actual displacement of the medium. We're talking like a longitudinal wave. So the compressions and rarefactions, kind of like the squeezes and pulls of that longitudinal wave as it travels forwards in space. So the solid line represents the system at time 0, showing like where the compressions and rarefactions are, and then the dashed line shows that same system that has actually traveled forward in space because the sound wave itself is traveling. It's a traveling wave, it is not a standing wave, which is kind of funny because often we see sound waves as standing waves, like in guitar strings or in air columns. But if you make a sound and it travels through the air, it is an oscillation along its axis, back and forth of compressions and rarefactions along its axis that then travels through space. So let me just describe, looking at the solid line, let me describe what it's actually showing. So we have an oscillation, and the center line right here, that is the equilibrium point where there's no displacement. And of course, you would have the amplitude points of maximum displacement here and here and here and here. And so, yeah, these would be x naught, and then these places here would be x equals 0. Or y, as the case may be, but like that's where the displacement of the medium is 0. And so we can have we'll have speed, no motion, v equals 0 at the amplitude points here, right there, and then we'll have the maximum speed happening here and here and here and here as we go. So looking at the motion of the graph, we have here and here as going from x equals oh, I'm sorry, that's the x-axis. Scratch that. Looking at the vertical displacement as it goes from 0 at those points there, we're kind of going down into the negative displacement. Now, again, it's not, the particle is not literally moving down. This is not a transverse wave, but if it's talking about negative displacement, where it says a displacement to the right of the equilibrium position is positive, then that means those 2 points there are going to be leftward movement. And then that's where the speed is maximum, so we have like a maximum leftward velocity or negative direction velocity there, which then that's coming up onto either a compression or a rarefaction, but that would be these points here. Let's call it a compression because it's 1/2 of the cycle. Compression. And at the compression, there's maximum acceleration, but there's no motion. We're considering that at the amplitude point, and we know that at the amplitude point, the velocity is 0, so it wouldn't make sense to say at the compression point whether the particle is moving left or right. But right after that, as we leave the compression and head towards rarefaction, at those points there, the particle is moving into the positive displacement, into the positive, stop erasing, thank you, into the positive displacements there, kind of going like up into the positive displacements. But again, it's not literally moving up because we're talking a longitudinal wave here, so we're going to say that is a rightward displacement, a positive displacement. And then that's going to bring us up to this part of the cycle, which would be our rarefaction, our point of maximum expansion. And then after the rarefaction, we moved to the left. The particle moves to the left to go to compress, and then it moves to the right to go expand to the rarefaction. In that kind of wom of like compressing and expanding, that system itself is not standing still in space. That would be a standing wave. Many sound waves that we see illustrations of or animations of just stand still and don't move. This says it's a traveling wave. So that system of compressing and expanding medium then itself travels forward in space, and that's why we have this second dashed line wave right there, where the entire system has translated to the right because it is in motion. I just wanted to explain that. That really has nothing to do with answering any of the questions. It doesn't. You don't actually need to write that or do anything with that. Actually, I think there is a question that kind of touches on it. But I feel that if you don't understand what this graph is actually trying to show you, you're not going to answer the questions correctly. So that's why I just wanted to explain it first, especially since if you miss this part right here, where it says a longitudinal wave is traveling, and you think that's a transverse wave, you're going to have a bad time. So there you go. All right, let me erase all that jazz so we can actually start answering these questions. And so in 11AI, calculate the speed of the wave. A very basic way, I would say the simplest way of doing this is to note that in 0.882 seconds, the wave itself has traveled this far, which is 0.3 meters. So you do 0.3 meters in 0.882 times 10 to the negative 3 seconds, because it's 0.882 milliseconds. That's 340 meters per second is our speed. There's another way of doing it, and I'm just going to throw this out there in case any of you actually try this. You can set up kind of like a ratio. You can, to solve for the period, because you can actually treat this as a v equals f lambda situation. I can see from this that the wavelength of the wave is 1.6 meters. It's the length of one full cycle. And then frequency I can get from 1 over the period. And then to get the period, I know I can say like, well, if the period is to 1.6 meters, I know that we have, what is it, 0.882 times 10 to the negative 3 meters in how many seconds? Oh, wait, I'm sorry, 10 to the negative 3 seconds, and the displacement would be 0.3 meters. And you can kind of set up a ratio there to figure out what the period is and kind of work all of that back. I think that's way more work than just doing V equals D over T, for Pete's sake. Keep it simple. Right? And then for the second part, we have 11I, and that's showing that the angular frequency is 1300 radians per second. So angular frequency, we know, is 2 pi over the period. And we know T equals 1 over F, and V equals F lambda, which both of those things are kind of SL stuff, but I also think that you should kind of know that and remember that, especially V equals F lambda. V equals F lambda is a big deal. If you don't remember much about physics, remember that. So if we combine all of that together, so throwing this all together, we have that the angular frequency is 2 pi times the speed over the wavelength. The speed we just found, and 11ai. The wavelength I mentioned before, but I'll show you again. One cycle right there is 1.6 meters. And so we wind up with an omega of 1300 radians per second as predicted by the problem. So there we go. There's another way of figuring that out, saying that if 0.882 milliseconds is like 0.3 over 1.6 of a whole cycle, you could set up a ratio of using that and then figure out the radians per second from that. If you did that, that would also work. I prefer using the equation that is actually attached to SHM. That kind of, I don't know. Now I'm thinking about it, it's like, yeah, but if you're talking about a portion of a cycle is also a simple harmonic motion. Whatever. This works. 1300 radians per second. Let's move on. Okay, so to answer 11b, I need the graph from the previous page. So I went back to the previous page and I grabbed that graph right there. And so me making reference to that. It says BI, state and explain the direction of motion for the particle at t equals 0. So we can see that for the t0 curve, let's see if my highlighter works. I don't know that it was working before. Here is there's the time 0 curve right there. And I explained earlier at the beginning of the video for question 11 that no matter what the position of the particle is, at time 0, the displacement is 0 and the particle is on its way to the negative displacement. Be careful, the particle itself is not on its way down. We said earlier that into the negative displacement means that the particle is moving to the left. So let's write that down for our answer. That's kind of like the state and explain, but really when it comes to state, it's moving towards the left. 11bi says show that the speed of the particle at 0.882 milliseconds is 4.9 meters per second. Well, let's refer to the graph. Of course, now I'm referring to this curve right here. This is the curve that goes with the 0.882 milliseconds. And the question referred to x being at 1 meter. And I see that the 0.882 millisecond curve meets 1 meter at that point right there, which on the vertical axis gives me a displacement of about negative 1.5 millimeters. I'm going to need that in my formula. All right, let's go back to the paper. So there's our equation from the data booklet. I don't need plus minus because there's no such thing as negative speed. So I'm just going to say omega. Why did I put a parentheses there? I don't need that parentheses. So I can say amplitude squared minus displacement squared. Omega we have already solved for. That was the 1300 radians per second. I really don't need to put units in. So that was the 1300 radians per second. Amplitude squared minus the displacement squared. The displacement's negative, but it doesn't really matter because it's going to be squared. So we can figure out the speed from that and rework the numbers through. We get that the speed is 4.9 meters per second, as predicted.